name is Sam Trost. I have a bachelor's in chemical engineering. I've spent the last year and a half working in the semiconductor industry as a process engineer, troubleshooting chemical management systems.
My name is Katie Cutelli. I have a bachelor's degree in neuroscience, and I've spent the past 2 years working in science, research, and healthcare consulting with a focus on protein folding and cancer.
My name is Patrick Macy Phelps. I graduated from Wesleyan University 2 years ago with a bachelor's degree in math and economics. I spent 2 years working in consulting in financial services.
My name is Jing Wang, PhD in neuroscience. I finished my postdoc from Sunrise School of Medicine. I had the biopharmaceutical company experience in the last few years. And today our topic is predicting the effect of genetic variants to enable the personalized medicines. So actually, like our team name is GCAT Teams. We actually very glad to have our team work together to present this talk. So first, I want to run through the presentation outlines. So Patrick and I will first give an introduction of the background and the motivation behind it, and then we will introduce the workflow of the whole project. And Katie will continue do the EDA and feature engineering part, followed by Sam, who will introduce more detail about the natural language processing and model selections. I will continue to do the implementation introduction about how we use the model to develop a production step. And finally, we will summarize about the whole project.
A brief introduction into our presentation today. Cancer tumors can have thousands of different types of genetic mutation variations, and the process for classifying particular genetic mutation variations as drivers or passengers of tumor growth is often a difficult and arduous process. So how this process typically works is a skilled oncologist has to read through numerous relevant scientific papers in order to figure out whether this particular genetic variant falls along a variety of classes and whether or not they would like to recommend gene therapy for this particular genetic variant. So currently this classification is being done manually, but Memorial Sloan Kettering Cancer Center opened up a public Kaggle competition asking the general public to classify variations using machine learning techniques across 9 mutually exclusive classes. So the end goal of this is to automate the prior arduous manual process of classifying genetic mutations in order to further inform gene therapy recommendations in cancer research. So, to give you a sense of the data that we were working with, we had a training set which had 3,321 different genetic variants and a test set with over 5,000 variants. The variables that we were dealing with are the particular gene and variation, as well as text from academic papers which oncologists use to identify the class of each genetic variant. So our goal was to use this text data, as well as any other data that we could pull on the particular gene and variant, in order to classify the genetic variants in the test set along this 1 to 9 scale. And then a brief overview on missingness. We didn't have to do too much with regard to missingness because only 5 of the observations had missing text values. That wasn't really an issue for us.
So I'm going to have an introduction about the project overflow. So Patrick already mentioned that we got the data from the Kaggle competitions. And first we try to do the data processing, pre-processing. And we're using R and Python to do the EDA. And Katie did the Shiny app, so we can have a more interactive way to look at the data. And then after that, we using the natural language processing to actually vectorize the text. And then we also did the SVD to reduce the dimension. So we can actually using the reduced dimension vector to process the machine learning algorithms. And then we follow we tried a bunch of machine learning algorithms. For example, like logistic regressions, random forest, also use XGBoost using the SVM. Also, at last we also use neural network, INN recurrent neural network and the convolutional neural network to do the text processing and try to make the best prediction as possible. And then we try to submit to the KO competition and to get the rank. But beyond that, we also try to test this model in a real-world situation. So what we think is, if we can actually get some new text from outside, from some medical website, medical research website, for example, like the PubMed research PubMed website, and if we can throw this text into our model, can we make any predictions? Can we give any recommendation to the medical researchers? So in order to get that, we did the web scraping using the surveillance, and then we threw the scraped data into a database prepared with the Jingo framework, and then we threw this new text to the model, and using the optimized model to give the output of prediction. And then we can have a prediction as well as some recommendation to show the user of our models. So that's the whole idea of our workflow. And next.
All right. At this point, I'm going to go more in depth into the data by looking at our Shiny app, which contains our work on the exploratory data analysis. To begin with, the data we were provided from Memorial Sloan Kettering included a large text file on each specific case, as well as a data frame, which you can see at the top here. The data frame contained initially information on each case ID, as well as each gene, each variation, and the class, which was our predictor. In addition to this, we ended up adding a few features of our own, including the original amino acid, mutated amino acid, elective, and hydrodiff, which I'll explain in a moment. One of the first things you'll notice is that for a single gene, it may be attributed already to multiple classes. For example, the CBL gene is already in 5 classes on this one page, so it's clear that gene alone doesn't provide sufficient information for classification. Some of the extra information must come from the variation, and so we focused on performing feature engineering on point mutations, which are the specific cases under the variation column in which the case begins with a letter, ends with a letter, and contains numbers in between. So what we did was we isolated the first amino acid, which is the first letter, under the original amino acid column. We isolated the mutated amino acid, which is what the original was mutated to. And then we merged this with a data frame containing additional information on the physiochemical characteristics of each amino acid. And what this allowed us to do was come up with the elective and hydrodiff functions, which tell us when the amino acid was mutated, was it changed to a different amino acid with significantly different charge and polarity characteristics? And if so, does this affect the overall function and structure of the protein? And so higher absolute values in the final 2 columns would indicate that the change in amino acid was most likely significant and would affect the overall function of the protein. To provide further information, briefly, we created a histogram to show that the electric diff and hydrodiff characteristics do vary across the data, so that we'll have some variation to look at. And then to take a further step back, we looked at the data entries for each class, and we noticed early on that we were dealing with unbalanced classes, with class 7 having almost 1,000 entries and class 8 having only 19 entries. And if we look at the top 12 mutation types by frequency, we see that by far we have the most point mutations, which is why we decided to focus on engineering that feature. But we also have a variety of others, such as deletions, truncations, amplifications, contributing to the complexity of the data. Notably, if we look at the top genes in the training test sets, we see that they're very different. So the top gene in the training set is BRCA1, whereas F8 is the top gene in the test set, and there appears to be no obvious overlap, which is something that we need to be conscious of when we're looking for gene-relevant words and we're examining our text data. The most frequent words by class. The most frequent words by class also show noticeable differences. However, there is some overlap. For example, classes 1, 4, and 5 all have a BRCT as the most common word. And so this is is a highly common word. So this is something that can help us examine the differences and similarities between classes. And if we look at a word frequency comparison chart across classes, which will take a moment to load. One of the things that we will notice is that we can compare one class to two other classes in terms of their word frequencies. And as you'll see in a moment, the words that appear, the words that appear in the bottom right, for example, in each case, are more common in class 1 or 3 than they are in class 2. So this is just an example to show you a visual way in which we can examine which words vary in their frequency across classes, and this can tell us something about this can give us a clue as to the particular words in each class. So P53, for example, is more common in class 1 than class 2. BRCA1 is more common in class 3 than class 2. And finally, if we're looking at n-grams, which are portions of words that are more than one word, for example, 3 words in a row, this can help us understand the context of the data better. So this would give us something such as star syndrome rather than just the word star or syndrome alone, CVL mutations rather than just CVL on its own. And so this helps us piece together the data overall. And now I'll transition to Pat, who's going to be talking about dimensionality reduction.
So in order to reduce the dimensions of some of our categorical variables, namely the number of genes and the number of unique variations, we use truncated SVD through scikit-learn in Python. So as you can see here, there were 1,507 unique genes and over 8,000 unique variations. This is too much. We felt that the sparsity would hurt some of our models. So we decided to use truncated SVD in order to reduce the dimensionality, and the number of components we chose for each variable was 25 gene components and 25 variation components. We tried a number of different combinations ranging from 50 components down to 5 components, and it might be notable that the combination of 5 gene and 10 variation components perform better when we just use these variables on their own in our models. But when used in conjunction with some of the text vectorization features that we use through our NLP techniques, we found that the 25-25 combo worked the best.
And now I'll be giving, thank you very much, a short presentation on count-based vectorization. So count-based vectorization involves how we divided up the words that we were dealing with. And so the simplest technique for this is something called bag of words, which is simply taking a corpus of text and dividing it up word for word, in which each word is taken to have equal significance and just analyzed for its presence. So a sentence will be broken up, and overall the counts of each word will be tallied. A more complicated version of this, which we ended up using for some of our models, was TF-IDF, which stands for Term Frequency Inverse Document Frequency. And what that means is that in cases where a term appears more frequently in a document, that is noted for having more significance. However, if a term appears in every single document, then that is penalized. In our case, words such as cells and cancer would appear in every single document. And so we wanted to cut through that noise and get to words that were rarer and overall would have more significance and allow us to distinguish between documents.
So one of the other word embedding techniques that we used is called doc-to-vec. Doc-to-vec is a word embedding technique that was invented by the same people who invented word-to-vec, Quackley and Thomas Mikolov over at Google a few years ago. Word-to-vec is a shallow neural network with an input layer, hidden layer, and an output layer that essentially creates a word embedding matrix or weight matrix through stochastic gradient descent and backpropagation, where it uses a one-hot vector encoding that is the center word essentially, and it tries to predict the probability of context words through a sliding window. Doc-to-vec is a little bit different in the fact that it also uses a paragraph matrix. That paragraph matrix for here is essentially just paragraph tags. So each document has its own tag. And that's called distributed memory because each paragraph tag also has the context of all the words inside of that paragraph. It also has a method called distributed bag of words, which instead of training the word matrix, only trains the paragraph matrix. We use both of these. So the first neural network that we constructed was just a deep neural network with dense, fully connected layers, seven of which had 512 neurons, and then the last two of which had 128 and 9 as the output. All of them had rectified linear units as the activation signals, and there were dropouts in between at smaller and smaller intervals. The output function had 9 neurons because there were 9 classes. The reason that you need the dropouts is because of overfitting and because of too much memory usage. The way that we constructed the architecture was through cross-validation, and it worked pretty well. The next neural network that we created was based off of a research paper entitled Medical Text Classification using convolutional neural networks, published several months ago by some researchers at IBM in New York, Ireland, and Japan. And the point of this paper was essentially to classify medical tests based on 26 different categories ranging from cancer to genomics to anything else in between. And they had a neural network that was architected this way, which was 2 convolutional layers of 256 layers each, followed by a max pooling layer with a pool size of 5, I believe. We had that going twice, there and there. Then we had dropout of 0.5, and then one fully connected layer of 128, followed by one final one of 9 instead of 26, because again, we had 9 classifications. And this performed about as well as our deep neural network. Obviously, if we want this to perform a little bit better, it would take tweaking because we use different data than they did. Okay, over to Pat.
All right, so we've talked about a number of the features that we've used in our various models. Sam outlined a couple of the neural networks, which were some of the more computationally heavy methods that we used, a little more math involved there. So now, hopefully this graph will give you a sense of the importance of the various features that we used. So in this first segment between the 2 red lines shows the importance of the gene and variation SVD features that we engineered. So obviously most of these are fairly important relative to the others. So we decided to keep these in for most of our models. The next red square shows some of the amino acid features that Katie engineered using some outside data. The first couple ones involving amino acid charge difference and hydrophobicity ended up being fairly important, so we included these in most of our models. But the specific one-hot encoded amino acid start and final features we decided to drop because these had relatively little importance. And then finally, this last red square shows the importance of our doc to Beck features. These we also decided to keep in. Okay, so this next slide is a little dense. I won't walk through all of the hyperparameters that we tuned, but if you're curious, this will give you a sense of the performance of the various models that we tried. With all of these models, we performed some type of cross-validation, usually 5-fold cross-validation. Some of our more successful models were the XGBoost model, where we used doc to Beck features representing the medical text. And this next column shows any type of text alterations that we used. So we had a dictionary of stop words, including and, the, while, when. So obviously, as Katie mentioned earlier, we don't want to incorporate these insignificant words in our analysis. So these were dropped from the end data set. Here shows the important hyperparameters. Let's see, another successful model was the support vector classifier. And then finally, this last column of notes shows how the models did at predicting various classes. So we mentioned earlier that our goal was to classify genetic mutation variations from 1 to 9. And so some of the more popular classes like class 7, some of the models like multinomial naive Bayes tended to loop a lot of the observations into this one very popular class. So we thought that this was not an ideal model to use because given the sensitivity surrounding cancer mutation classifications, we thought that we choose a model that was more balanced in its predictions, right? So we thought that the XGBoost model was more successful at predicting the accuracy of all classes. And a way that we can see this is just through a simple confusion matrix at the end of each process. Okay, this next slide shows the success of the neural networks that we ran. As we mentioned earlier, one of them was run using TF-IDF text vectorization. The other two were using doc2vec. Let's see, this last one shows the neural network that Sam described in his most recent slide, which had 2 convolutional layers. This was one of the underperforming models, but we felt that this one had the most research-based justification given that our model construction was based on some researchers who had done this procedure before. So one thing that we might do in the future is run some different neural network constructions with different amount of layers and different amount of convolutional layers. And now for some broad takeaways from the models that we ran. We found that our models tended to confuse classes 2 and 7, as well as classes 1 and 4. So this might be an area where oncologists might look to tweak our models and find out which specific words are most helpful in differentiating these 2 classes. This is an area where maybe some more domain knowledge might be helpful. Another thing that we found was that changing the class weights equal to balance tended to reduce the accuracy of our model, but fixed the problem of over-predicting more popular classes. So, like I said before, given our task at hand, we chose to leave in class weights equal to balance for a majority of our models. Like I said before, XGBoost was our most effective machine learning technique, and doc2vec tended to be the most effective text vectorization technique relative to TF-IDF for Beck words. So lastly, we did an ensemble of 8 of our more successful models, and unfortunately this ensemble of models performed worse on Kaggle, but we thought it was a useful exercise in order to average the predictions of everything. And lastly, we did a stack of 5 of our more successful models and threw the outputs of each of those models into a multinomial logistic regression function. That also performed a little worse than our best XGBoost model in the Kaggle competition, but I think with further testing and maybe using a few different stacking techniques, we might be able to improve on that score.
Okay, so since we have a model, we actually practice a lot of modeling technique, and we beyond just submitting to the Kaggle competition, we try to expand our scope a little bit wider. So we try to test our model and build a proof of concept pipeline to use our model, make some prediction on new text. In order to do that, we using the Python Selenium technique to scraping a lot of new text from the PubMed website. And this website has tons of medical research papers over there. So we input the keywords, any keywords, some keywords, cancer-related research, and we scraping over 37,000 cancer research abstract from the website. And then after we got this abstract, and we built a database systems using Python Django framework, and then all the abstract and all the titles was inside the database, and then we use automated method to extract this abstract, and using this text put through into the model and try to use the model to make some predictions. And then after we made the predictions, we upload these predictions back to the database. And now we can actually not only see the list of abstract, but also for each abstract we can have classifications. And beyond that, we also use the doc2vec method to vectorize the text, and we also can make some recommendation for each research abstract. So what we do is we can input the text, or we can actually just use the title, input the database, and then we can make some recommendation. The output will be extra paper which most related with the selected paper. Okay, so here I want to summarize the project. So we finished a lot of EDA and feature engineering, also through the text into the pre-processing, and try a lot of natural language processing and machine learning algorithms. And we also submitted to the Kaggle competition at the media ranking scores. Also, we also built a pipeline and a prototype for using the new text, and try to testing not only the algorithm but also how this whole algorithm using the whole algorithm database and to output some predictions can help the researchers to make better decisions. So there's some future works, and Patrick can have some future.
Yeah, so I think one of the main takeaways from our project here was that we didn't just build a bunch of different models and see which worked better on the Kaggle dataset. We took a holistic approach and tackled this issue from start to bottom, right? So Katie put together this wonderful Shiny app which oncologists can use to look at the differences between classes by the different words that are common for each one, right? Or take a look at different features, and they could toggle through those tools. And also the Django database that Jing put together. Oncologists can, for future academic papers, just plug in the text of a paper and immediately see which class it falls into from 1 to 9. So I think better than the models we constructed, we really tried to tackle this problem and offer some potential tools that oncologists can use in the field. So yeah, a few things that we noted, some future things that we can work on. We might try to explore some more machine learning techniques using the doc to Beck feature, because that seemed to be the most important text vectorization technique. We might try to do some more model stacking and ensembling. And finally, we could further refine our research engine and keep updating the database that we put together in order to keep the data flowing, keep our models working better, and update it as doctors find new genetic mutation variations. Thank you. That's it.